So we'll use this transitivity in a bunch of examples to check what leads to what in those examples. Our first example would be the simple random walk on, say, 0, 1 to 5. Doesn't matter whether you take 5, but we just decided to choose 5 with reflecting barriers. Now, you may not remember what it is, so let's quickly look at the transition diagram. So essentially, it says that it's a simple random walk only, except that at the barriers, which is 0 and 5, at the boundaries, it gets reflected. So if it's somewhere in the middle, somewhere in the interior, it just performs simple random walk. So it moves to one of the neighbors at random with equal probability. However, if it reaches 5, say, it immediately gets back to 4. Similarly, if it reaches 0, it immediately gets back to 1. Now, in this case, we see that it's clear that each state leads to its neighbors. Now, of course, I'm writing neighbors with S in the bracket because 0 only has one neighbor, and so does 5. But others have 2 neighbors. So each state is going to lead to its neighbor. And everything is connected here in this graph. So therefore, this shows that by transitivity, take any 2 states, one leads to the other. Okay? You can start from wherever you like and reach wherever else you want to go. Okay? So this situation is a very nice situation. This is called an irreducible Markov chain. So in this case, this Markov chain is therefore irreducible. Since we are talking about simple random walk with reflecting barriers, we should also talk about simple random walk with absorbing barriers. Say it's on the same set, 0 to 5, it doesn't matter. Now this can be observed, for example, if you look at Gambler's Ruin, where one gambler starts with rupees 3 and another one gambler starts with rupees 2. Okay. So here the transition diagram is more or less the same, except at 0 and 5, sorry, and except the boundaries, the barriers. If it reaches 0, it just stays put. The next step is coming back to 0 over and over again. Similarly, if it goes to 5, it just stays put. So in other words, P00 and P55 are both 1. Okay? Last time, whenever you reach the boundaries, you get reflected to the next neighbor. Here you don't do that. You just stay put. So one thing that you can easily observe is that the states 1, 2, 3, 4 lead to all the states. This is because they just go to any of their neighbors. Okay, each of them have two neighbors. All of them lead to all of their neighbors. Okay, so therefore they will reach any state in the graph. Okay, the 0 and 5 can be reached from 1 and 4 respectively, and therefore everything will lead to 5 and everything will lead to 0 by transitivity. So 1, 2, 3, 4 are nice states. They lead to everything. However, 0 leads to 0 and 5 leads to 5 because P00 is 1, P55 is 1. Not only that, if you start a Markov chain at 0, there is no way you can get out of 0. Same applies to 5. If you start the Markov chain at 5, there is no way you can escape 5. So therefore, 0 and 5, they do not lead to any other state. Clearly, this Markov chain is not irreducible. This is because 0 and 5, they do not lead to any other state. We will soon see that these 2 states, 0 and 5, they are called absorbing states. And the Markov chain gets absorbed in these 2 states, either of these 2 states. Okay, so another example, this is another trivial example, is the deterministically monotone Markov chain. What is that? That's just the Markov chain that starts at 0 and then moves to 1. And from 1, it moves to 2. And from 2, it moves to 3 and so on. So this is the transition diagram. It's a trivial transition diagram. It's deterministically monotone, so there is nothing random about it. However, it's good to look at this Markov chain and try to understand the new notions that we learn. Now it's clear that each I will lead to I plus 1. So everything will lead to the next guy. Of course, each I will lead to I also, because this leading to relation is reflexive. So therefore, what it says is that whenever you have two states I and j such that I is less than or equal to j, I will lead to j by transitivity. So from 1, you can go to 2, and then from 2, you can go to 3, and then from 3, you can go to 4. Therefore, 1 leads to 4 by transitivity. So therefore, whenever I is less than or equal to j, I leads to j. Note that if I is strictly bigger than j, there is no way I can lead to j, because here leading to happens only towards the forward direction, only towards the right side. The Markov chain only moves towards the right side. There is no going back. So therefore, I leads to j if and only if I is less than or equal to j. Obviously, this is not irreducible, because, for example, 4 does not lead to 2. Okay. Now, another example is the simple random walk on integers. Just quickly remind yourself what is the transition diagram. Here, wherever you are, you just move to one of the neighbors uniformly at random. So every point has 2 neighbors. You just move to one of them with priority half. Again, since each point leads to all of its neighbors, by transitivity, it follows that this Markov chain is irreducible. Anything can lead to anything. Everything. By the way, this entire graph is connected. So therefore, whatever I say is correct. Now, the same logic would apply to simple random walks on all the other groups that we have seen, namely Zn, Zd, the discrete cube, Z2 power d, or the free group F2, everything. In all of them, what is common is that every point leads to all of its neighbors. And the entire graph is connected, and therefore, every point will lead to every other point, and the Markov chain will become irreducible. Now remember that our goal was to obtain a decomposition of the state space based on the evolution of the Markov chain. Now decomposition just means a partition, and we know that any partition comes from an equivalence relation, and any equivalence relation gives rise to a partition based on the equivalence classes. Okay? So therefore, what we need is an equivalence relation. However, this leads to relation has a problem. It's reflexive and transitive, but it's not symmetric. So we are almost there, except that the symmetry is not available. We just symmetrize it. That's the solution. So we'll just symmetrize this relation to get a symmetric relation, and that will be an equivalence relation. So this motivates the next definition, namely the communication relation. So we say that I communicates with J and write I double arrow J, okay, or we'll just read as I communicates with J if I leads to J and J leads to I. This is just the symmetrized version of the leads to relation. That's all. Therefore, it's not surprising at all that this relation is indeed an equivalence relation. Namely, for all ij, k in S, the following will hold. I leads to I, that's the reflexivity. I leads to G, I communicates with I, that's the reflexivity. the communication relation. I communicates with J will imply J communicates with I. So that's a symmetry. Now I communicates with J and J communicates with K implies I communicates with K. So there is a typo here. The statement is correct, but this should be communicates. Okay? Because we are talking about the equivalence, this being an equivalence relation, this should be the transitivity of the communication relation. This statement is true, but there should be double arrow here. So I'll correct this time. Okay, so now the proof of this is very simple because reflexivity of the communication relation just follows from the reflexivity of the leads to relation. Same applies to the transitivity. And symmetry is just tailor-made. You know, the way we have defined it, it has to be symmetric. The relation has to be symmetric. We just symmetrized the leads to relation to get this relation. So therefore, it has to be symmetric. So this shows that communication relation is indeed an equivalence relation. We'll of course correct this typo here.